Ambassador Program is a stormwater education program in partnership between Martin County and University of Florida IFAS Extension Florida Sea Grant Program. We have a monthly webinar series. So you can see our upcoming talks for August and September are on sea level rise simulations, as well as Martin County's integrated watershed master plan development. We will be sharing the registration links in the chat for you in case you haven't registered for these yet and you're interested. And if you are unable to attend live, we do record all of the presentations and they are available on the Martin County YouTube page. We will also put this link in the chat. And we have the playlists from not only 2025, but I think we go back to 2022. So we've got 3 or 4 years worth of Water Ambassador webinars for you to watch based on your interest.
Actually, 2020, Lisa.
Oh my goodness, many years. We will be taking questions, but we ask that you write your questions in the chat as they come to you, and then we will be holding those questions so we don't interrupt our speaker, and we will do all of our question and answer at the end. So please make use of that chat feature. And with that, I am really pleased to introduce Nathaniel Winn, who's going to be talking to us about assessment of water quality trends and environmental stressors through 25 years of citizen science. Nate is a researcher from the Florida Oceanographic Society, studying marine macrophytes and macroalgae, anthropogenic impacts on water quality, marine community ecology, and biogeochemical interactions in estuarine ecosystems. He received his BS at the University of West Florida, where his research focused on submarine groundwater discharge and porewater nutrient cycling. He received his MS from Florida Atlantic University, where he studied the internal oxygen and sulfide dynamics in tropical seagrass species in Florida Bay. His background also includes extensive work with GIS and remote sensing tools to monitor surface water quality and harmful algal blooms. His current work focuses on the biological resiliency and interactions among Indian River Lagoon seagrass species and examining long-term water quality trends in the St. Lucie Estuary and Indian River Lagoon, which is what he's going to be presenting on today. So with that, I'm going to stop sharing my screen and turn it over to Nate.
All right, let's see if I can get this pulled up. Okay, perfect. Well, thank you for that lovely introduction. And yes, hello. Hi, everybody. My name is Nathaniel Winn, as Lisa stated. I'm a researcher at Florida Oceanographic Society. But in addition, I just wanted to quickly shout out Florida Oceanographic. In addition to doing seagrass and water quality, we're also doing some great research that pertains to oysters, bivalves, community ecology, and a lot of different things that focused on restorative ecology, as well as at Florida Oceanographic, we have an awesome education team at our coastal center and a great advocacy team. So yeah, after that quick plug, I'll go ahead and focus on what we're talking about today. So we'll be focusing on water quality, and I'm going to be presenting a project that I've been working on, which is assessing water quality trends and environmental stressors using 25 years of citizen science. Here we go. Okay, so just to start off with some background information, we know that water quality is vital for maintaining ecosystem functionality and health. However, with continuous anthropogenic development on coastal watersheds, it can cause significant ecological changes. Changes such as coastal erosion, changes in freshwater distribution, and increase in nutrient inputs. You can see here the picture I included is just a classic example of a Florida coastline from 1925, increasing its development tremendously to 2016, drastically changing the way the coastline looks, and with all this development definitely impacting the nearby estuaries. And so these impactful ecological changes that come with coastal development can actually cause our nearby estuaries to experience more eutrophic conditions, such as the production of large-scale phytoplankton blooms or algae blooms, which can create more acute effects, such as fish kills and the mortality of other marine species and shellfish. And then can also cause more chronic effects, such as the loss of seagrass and other foundational species that ultimately result to habitat loss. And this water quality degradation is especially true and has been experienced in parts of the Indian River Lagoon. So again, some background. Indian River Lagoon, of course, we know is located on the east coast of Florida. It extends 156 miles all the way from Ponce Inlet down to Jupiter Inlet. And because of its vast size and a little bit differences in hydrology, it can be kind of segmented to different parts of the Indian River Lagoon. So you can see the map I included here from Adams et al. 2024. Breaks up the lagoon as the Banana River Lagoon area up in purple. Mosquito Lagoon's not covered in this graph, but is up there as well. You have the upper north IRL that covers the Melbourne area. The lower north IRL, or also called the middle IRL, that covers Sebastian. And then finally, the area that we're going to be talking about and focusing on today, the southern Indian River Lagoon that encompasses Fort Pierce Inlet, St. Lucie, and down to Jupiter. And around the southern IRL, we also have the St. Lucie Estuary. And so the St. Lucie Estuary intersects the southern IRL near the St. Lucie Inlet, and it brings fresh water from the St. Lucie River to the Indian River Lagoon, creating this brackish gradient of water, which brings a lot of diversity to the South Indian River Lagoon and the St. Lucie Estuary. And the Indian River Lagoon as a whole, including the St. Lucie Estuary, was once one of the most biodiverse estuaries in North America. But however, from coastal development and water quality degradation, it has noticed a significant loss in that biodiversity. And one thing I would like to focus on in this area is the anthropogenic impact of a large influx of freshwater inputs. So in this specific area of the South Indian River Lagoon and St. Lucie Estuary is we have a network of man-made canals that connects Lake Okeechobee all the way to the Atlantic Ocean. And during times when Lake Okeechobee levels are high, the Army Corps of Engineers will release these freshwater discharges, bringing immense amount of freshwater through the St. Lucie Estuary. And at times of high discharge rates, we can actually see it push into the proper lagoon and through the inlet. So this is something that's unique to this area that is, an anthropogenic stressor that definitely puts a lot of weight on our water quality. So because of the noticeable decrease in biodiversity and coastal development, a lot of different organizations along the Indian River Lagoon have developed these systems or networks to monitor water quality and try to help identify areas to where degradation is occurring. So for example, we have the Indian River Lagoon Observatory Network, also known as ERLON. It is maintained and operated by Florida Atlantic University, Harbor Branch Oceanographic Institution. And so, their network was established down in the South IRL around 2015, 2016. And these are what are called autonomous systems, meaning they're self-operated, they're programmed to take measurements every hour on the hour, and they collect their water quality data using a series of probes and sensors. And that data is then transmitted through telemetry online to a dashboard. So you can actually view real-time data from that network. Another similar example is the Kilroy network. This is maintained, operated by Team Orca. Down in the South IRL, we can see Kilroy sites were established early as 2020, 2021. And again, this is another example of an autonomous system taking those parameters, recording every hour on the hour. And then finally, a very prevalent water quality observation team has been the South Florida Water Management District down here in the South IRL. They've been doing this for a very long time, since the 70s and 80s, and then it became, their sampling just kept getting bigger through the years. And they go out on a monthly basis to multiple sites across the St. Lucie Estuary and IRL, and they collect they capture both measurements in the field with sensors and devices, and they also take grab samples to take it back to their lab for further processing. So we have these well-established water monitoring networks and teams out there. But there is one other one that I'm going to be covering today, and that is Florida Oceanographic's water quality monitoring program. So in 1998, Florida Oceanographic Society established a citizen science water quality research program titled FLOWS. Stands for Florida Oceanographic Water Ecosystem Surveys. And the main purpose of this program was to capture long-term water quality data to cover both spatial and seasonality changes in our estuary, as well as to see how our water quality is being impacted by anthropogenic stressors such as Lake Okeechobee discharges and the potential production of algal blooms. And why in 1998? Well, during that time, we were having one of the largest discharges coming from Lake O that was occurring in 1998. And this large amount of water entering our estuaries were causing some environmental concerns, production of algal blooms, and just overall degrading the water quality. So this encouraged Florida Oceanographic to start this water quality program to help try to identify key areas that might be affected, and also show how exactly our waters are being affected by these anthropogenic stressors. So this, program back in 98 began with just a couple of volunteers that really wanted to make a difference. And they would go out to the end of their docks, their private residence, and collect water quality samples, every afternoon after work or once a week. And then now to present day is just involved to this large scale research program with many, many dedicated volunteers testing all across the St. Lucie Estuary and the Indian River Lagoon. So it's really amazing of how looking at how this project has evolved to current day. And so over the last 20 plus years, our water quality volunteers have gone out to their assigned sites to collect an assortment of both physical and chemical water quality parameters throughout the lagoon, to which you can see on the table here above. And some of the sites that we have our water quality volunteers at are public. So a lot of them are public boat ramps and public parks that have water access. But also we have a lot of our volunteers that are testing at their private homes from their docks. So having both private and public land that we're able to monitor the water quality from very much expands our data range, which is great. So looking at the table, just some of the parameters that we collect. We collect salinity via the refractometer, dissolved oxygen using a modified Winkler titration, pH, phenol red color test. We do temperature, visibility, and water depth using Secchi disk, however you wish to call it. And then also just kind of other parameters that refer to the site itself, like what are the weather conditions, tides, surface water conditions, as well as, whether there's presence of an algal bloom or petroleum sheen on the surface, we've asked our volunteers to take great note at each one of their testing sites each week. So our volunteers are truly the eyes and ears at their testing site and around the lagoon. And because we have them test in both saltwater, brackish water, and at sometimes complete freshwater environments, we get a lot of variability with the data that we get back. So early on when this program was established, we needed to create a specific zones that would have sites that had related water quality to them. So we needed to basically map out and zone out our water quality testing area. So that's exactly what we did. So here is an example of our Florida Oceanographic water quality testing zones. So you can see that we cover majority of the St. Lucie estuary and just the southern portion of the South Indian River Lagoon. We don't typically go further than the county line up in the Indian River Lagoon. We go a little bit above the Jensen Beach Causeway, if you know where that is, but we have not yet expanded north from there. But you can see that, zones 1 and 2, we're covering the North Fork of the river, 3 and 4, the South Fork, 5, 6, and 7 are the middle estuary portions of it and Manatee Pocket. And then finally, 8, 9, and 10 covered the inlet area and the IRL proper. And so all of our testing sites are dispersed among these 10 zones, and to which you can see an example of some of our testing sites that we have here. So this is only a snapshot of our historical sites. There's definitely more than this, but cumulatively, we've definitely had over 110 established water quality sites collecting data from in this region. And, some of the sites, the timeframes vary. We'll have some sites that are only active for about a year or two, while other sites have started at the beginning of this project and we still are collecting data from, which is incredible. So the volunteers at each one of our active water quality sites are collecting data on a weekly basis, and they're sending us our data for us to use. And the main application of the data that's being collected now goes towards our weekly water quality report card that we construct. So this weekly water quality report basically assigns a letter grade to each zone based on the criteria of select parameters that just relates to general ecosystem health. And then so each zone maybe have different characteristics. So the criteria for things like salinity, visibility, and such will be different depending on what zone that this tester is in. And we'll take this report card and post it, publish it on our website and share it to the community. In addition, we also take this data and we compare it against previous years. So we've taken our letter grades. What you're seeing here is we're having our letter grades on our, let's see if I can get my pointer started. There we go. So we have our letter grades here, and we're seeing 2 years, 2023, 2024. This is just an example of some of the stuff that we publish with our report. We keep track of how it's changed from year to year, as well as how the report grade changes depending on anthropogenic stressors and other hydrological events, such as the inflow of fresh water from the C24, 23, and 44 in Lake Okeechobee. So this is an example of one of the graphs that we put on our report as well that shows in the black line our letter grade and how that's affected with these different shapes in the background, which are freshwater inputs from different sources. So to see how our water quality is impacted by increasing water. So that's just some of the examples of what we put on our report. But when I joined this program, when I was put in charge of this program about 2 years ago now, I wanted to know if somebody went further back, if we're not just, looking from year to year, if there was some kind of long-term analysis that was done. And I found a little bit of evidence, but no one has put a large collective analysis together. So that's what I wanted to do when I started this project. So just to emphasize this. We've been collecting data from this program for 25 years, and that is a tremendous amount of data sheets to cycle through, different data points all throughout the years. But, one thing I realized is our water quality program predates some of these other monitoring systems that are established today, like the Erlon and Kilroy. We have water quality data that can go back further. So I wanted to see if I could take the citizen science data that we've been collecting for 25 years, go back further in time to see exactly how our estuary has changed from coastal development, anthropogenic stress, and climate change. So that's what I sought off to do. However, oh, come on. There we go. However, it was important for me to first validate the data before using it. This, this is citizen science data. And, before I start putting it in models and trends, we definitely want to make sure that it is valid and it's accurate. So before even using the data, my first objective was to evaluate the validity. And then once I can show that it's valid, my next objective was to examine the historical water quality parameters and trends using the data. So that was my objectives. So how was I able to take 25 years of citizen science data and validate it for accuracy? Well, one thought is I could compare it to some of these systems that are up and operable today. So that led me to my first question, which was, how does the citizen science data that we've been collecting compare to some of these other monitoring systems? So that was my first research question for this project. And so I sought out to find what monitoring systems overlapped with our testing zones. So if we look back to this image I showed you with all of our historical testing sites, I needed to find monitoring zones that overlapped with our testing zones. So first, I looked at all of our Erlon data, definitely have some great coverage. A lot of same testing zones overlap with the Erlon stations. I also incorporated the Kilroy stations. And finally, to ensure that I had every single testing zone overlapped with a reference monitoring system, I incorporated the data, the monthly data that was collected from South Florida Water Management District. So I had my 3 reference systems to compare against the citizen science data. So how exactly am I going to take this and validate it? Well, first, I ran what's called a Mantell test. And a Mantell test, it's a multivariate analysis that can be used to calculate corresponding positions of 2 data matrices. So it will tell us how related the 2 data sets are based on their position, the parameter, and the time frames. So based on given all those parameters, it'll tell us how correlated these data sets are to each other. And so the main output that you'll get from a Mantell test is you'll get what's called the correlation coefficient, or R. So having an R value that is closer to +1, it indicates a strong positive correlation, which means the 2 data sets that you're comparing are very related. As one increases, the other increases. Rather, if you get an R value that's close to -1, it means that there's a strong negative correlation or a negative relationship, basically meaning as the data from one monitoring system moves in a certain direction, the other one goes the opposite direction, which, would indicate that they're not really related, or at least they're negatively related. And then finally, you have R's equal to 0. It really means there's no relationship to begin there. They're not really related at all. So I went ahead and took all the data from the reference systems and our citizen scientists, and I ran this Mantell test. So here are the results. I'm going to explain what you're going to see here. So what you're going to see is multiple columns. Each column is going to represent our testing zones. We have 1 through 10. And then each row is going to be a reference monitoring system like Erlon that was compared against our citizen science data for each zone. Anytime you see a blank cell, that basically means that monitoring system did not occur in that testing zone. And then this is an example of the output down here. You have your R value, which shows you what the relationship is. And you'll also get a P value, which explains how significant the results are. So here are the results. And just by looking at majority of the cells, you will see that all of our R values are greater than 0, meaning showing that there is a positive relationship there. You'll notice that some of the R values are greater than others. For example, you can see in the 2 circles here that we had some R values that were less than 0.5, which means kind of not too strong of a relationship there. And this occurred in Kilroy system in zones 7 and 8, which are the inlet and manatee pocket. One of the reasons why we think that maybe there was not a strong relationship here is the sample size was pretty small. These Kilroy systems, we were only able to retrieve data from 2022 was about the latest we could get. So it could be just the 2 years of data we had didn't compare well to each other. But also notice that all the P values in this test show they're less than 0.05, showing it's statistically significant. These results are. But overall, a quick summary of the Mantel test. Over 70% of all the comparisons made in this test scored above a 0.7 R value, indicating a really strong positive relationship. And even over 10 was above 90. So a lot of these, a lot of our citizen science data were very positively related to these other monitoring systems present in these zones. So yeah, from the Mantel test, we were able to show that there was definitely a positive relationship, but we wanted to further test to see how they compare by examining the difference in sampling intervals among the monitoring systems. So if you recall, we have our weekly volunteers that are collecting water quality on a weekly basis, right? South Florida Water Management District, for example, collects water quality on a monthly basis. And then we have those autonomous systems that are recording every hour and sometimes even less than an hour. So we wanted to see that even if we have these differences in time frame, does our data still match up and compare well to each other? So that's exactly what we did. We've ran this comparisons with many different years against many different zones. Here I'm showing you an example of the of one of the zones. This is in our zone 5 data from 2024. And what you're seeing here, I'm going to show you a series of 4 graphs, and each graph represents a different water quality parameter. On the x-axis down here, you have over the time in 2024. You have temperature on our y-axis, but it's going to be the whatever parameter we're talking about. And then you'll see we have 3 different series. We have our FOS water quality testers, our weekly in red. We have our hourly, or Erlon in blue, and we have our monthly water management district in green. So first off, let's look at temperature. We can see that throughout the year of 2024, all of these systems these box plots are pretty packed together. We're looking for the greatest amount of overlap. And for majority of these time points or these month points, we can see that there is great overlap between monitoring systems. They follow the same trend as you would expect: warmer in the summer months, colder in the winter months, and really clustered, or they're not clustered, they're packed together. So showing that there's a lot of relationship between there. Next, we look at dissolved oxygen, and you can see the same thing. Very niche, tight together, following the same trend. We expect to see dissolved oxygen getting a little low during the summertime when temperatures are high, and a little bit more elevated in the wintertime, but overall following the same trend and an extreme amount of overlap. For salinity, salinity was a little bit more variable, especially during 2024. We had the Lake O discharges, so there's a lot more bigger box plots, a lot more availability. But overall, you can still see a lot of overlap between all three monitoring systems and following the same overall trend. But this wasn't always the case. For example, here's what pH looked like. You can see that at some points that pH, our water quality pH was definitely more elevated than some of these other monitoring sites. And one of the reasons why this could be is just differences in sampling method. So those, Erlon stations and South Florida Water Management, they're using probes to capture pHs, while our volunteers are using phenol red color indicator. So this little disconnect could be a result of a difference in methodology. But one thing to note, it's also interesting that we got pretty good cluster or pretty good pairing with each other during the winter months. But in the summer is when we summer and springtime is when we saw that disconnect, which we're not really sure why, but it's very interesting. Yeah, so looking for the most part at the sampling intervals or looking at the difference in sampling intervals, we still see a lot of overlap and following the same amount of trend. But finally, we wanted to compare our data by examining what the citizen science data compared to Erlon data, how it responded to environmental stressors, such as freshwater discharges or maybe the presence of an algal bloom. Did they respond in the same way to these stressor events? So our first example I would like to show you is freshwater discharges. This is last year in 2024. We had a discharge event that was occurring from about mid-February to late March, putting freshwater down the C-44 canal and entering into the South Fork of the St. Lucie Estuary. And so what I've done here is I'm basically looking at salinity in both our citizen science data and in the Erlon data and seeing how they compare to each other. Were they able to capture this event? And so here we can see our graph. So you can see, so explaining this graph, down here is the x-axis. This is over time in 2024. Salinity is on our y-axis. And we're looking at two different monitoring systems here. We're looking at our citizen science in red that are taking weekly measurements as a reminder. And we have our Erlon station in blue. And one thing, and then the two vertical dashed marks indicates the stop and start date of these discharges event in 2024. So what you will notice is as both systems approach the start of the discharge event, they're both mirroring each other, following the same trends. And as soon as we hit the start date, that first dashed line, both systems immediately reach zero and follow similar patterns all the way until the end date, to where both systems rebounded immediately with almost zero lag. You can even, if you recall, during last year, the Army Corps of Engineers were actually pulsing the discharges, meaning that some weeks they would release more water than prior weeks to kind of make sure there wasn't a constant flow. And we can actually see both systems capturing that pulsing event, which is really incredible, that given that these two systems were on different sampling intervals and different methodologies, that we're both able to capture this stressor event. Another example is looking at a small hypoxia event that occurred in 2016, the St. Lucie area. It was like the middle of the estuary during an algal bloom. So there was an instant where dissolved oxygen dropped below 5 milligrams per liter. So we wanted to see if both systems were able to detect that. So here, again, we're looking at two systems. We're looking at our citizen science in red and our Erlon station in blue. This is during 2016. And dissolved oxygen is on our y-axis. The horizontal dashed line indicate measurements above or below 5 milligrams per liter. And as you can see, for the most part, even when we're looking at a different parameter, we're not looking at salinity this time, we still see the results of the dissolved oxygen following the same trend of what the autonomous system. I will say we did, just because of sampling interval, that there was a possibility that we missed a low point here in the dissolved oxygen, and that's just because of the difference between weekly and hourly data that's being captured. But based on the trends, we would be hopeful that we might have caught that if it fell within the week-to-week sampling period. But back to our main question, how does citizen science data compare to the other monitoring systems? Well, we showed by the Mantel test that they're all pretty, our systems compared to these other monitoring systems are pretty positively correlated to each other, regardless of the differences in sampling intervals, as well as they both respond similar to environmental stressors. So the next step and the next question I had in my project, my mission, is now that we were able to validate the data, I wanted to use it to see how had the SLE and the IRL changed over time using the citizen science data. So I will go ahead and give a fair warning that we're still working on this. There's a lot of data to go through and a lot of different things to test. So, yeah, and depending on what variable you look at, there's a lot of variability, such as like pH is a lot more variable to see how it's changed. But one thing that I want to focus on and share with you today that I took a deep dive on with this question here is focusing on temperature. So I used the citizen science data over 25 years to see how the temperature in our sampling region has changed. And I am here to show you that we actually have seen quite a bit of a temperature change. This is a GAM model, a generalized additive model, and basically it's taking the temperature in all of our sites across all of our testing zones and measuring how much the temperature has increased across these 20 years. And as we can see, just looking at this graph, that there's been quite an increase in temperature, especially during the period of 2007 to 2014. There is a steep gradient of a temperature incline. So, this leads me to question what event had taken place during this time period. And if you notice, overall, I mean, it's above a degree Celsius, almost 1.5 degrees Celsius of an increase, which may not seem like enough or a lot, excuse me, but a whole temperature, a whole degree Celsius increase of a temperature change, could be affecting certain biological processes that could be occurring in our lagoon. And this might have implications for disrupting or just changing or affecting certain processes that go into our lagoon. So this is very interesting when we found this and continuing to work through the data to figure out especially what happened between 2007 and 2014. But I took it a step further, and I didn't want to just see if the temperatures changed over time, but I wanted to see how it has changed across seasonality. So again, this is temperature. Down at the x-axis, this is months of the year, temperatures on our y-axis. And here you'll see a series of lines that are on a color gradient. Okay, more blue lines indicate more historical years, while more red lines indicate more recent years. And so just by visually examining this graph, you can see that our more historical years in blue are, the bell curve of this is extending when we move towards the more red lines. So we are able to see what we saw in that first graph of the temperature, the bell curve of the temperature increasing throughout the years. But not only that, I want to draw your attention to our winter months. Notice in the winter months that, you know, the earlier years in blue are a lot more variable, moving around. Some winters were hot, some winters were cold. But as we move to present day, you see a lot of that variability disappear. And it's a lot more streamlined as well as increased. So we're losing some of that variability with the winter and changing in the seasonality with our temperature distribution, which is very interesting. And then lastly, that I would want to talk to you guys today, still focusing on temperature, is we've had testers over the years that have collected samples during the nighttime. And it's not throughout the all hours of the night. It's more of late evening towards 10 p.m. And we'll have some very early morning before the sun rises. So with the little temperature, nighttime temperature data I had, I wanted to see if we could observe a difference in daytime and nighttime temperature across the 25 years. And so this is very preliminary of what I'm showing you, because I would like to rework this a little bit more and definitely bring on some of these autonomous sensors that are able to measure all throughout the night. But even just taking a look at some of the nighttime temperatures that our volunteers have captured, we've seen that, you know, daytime in red is increasing, but we also see this big jump in nighttime temperatures as well. And it's right around that same kind of position where 2007 area to 2014, we see this shift up in nighttime temperatures. And again, this is preliminary, and I plan to kind of move forward with this, you know, figuring out with more data across the entire lagoon. But if we're seeing this nighttime warming effect, that could have many implications for you know, affecting marine life, especially you know, those that depend on temperatures to drop during the nighttime to do certain biological processes. Another thought that comes to my mind when I look at this is, we know during nighttime, you know, there's not a lot of photosynthesis that occurs, and you know, we mainly just have cellular respiration, which is using oxygen. So our oxygen, you know, is typically lower at nighttime. But you know, if we have increased nighttime temperatures, the respiration rates are only going to increase, which is going to take more of that oxygen during the nighttime out of the water. But again, this is just some of the implications that might come out of this for the nighttime temperatures. So as I mentioned, you know, there's a lot more stuff a lot more things I have to do with this data. I'm super excited. I was able to share some of it with you guys, and there's a lot more that we can take from this. And so just some key takeaways from this project that I've been working on. We were able to take 20 years of citizen science data and kind of show of it being validated towards the other monitoring systems that we have up today, which was huge. And then using that citizen science data, we showed that the temperature in our system has definitely increased over 25 years, especially the winter temperature and possibly nighttime temperature. So very interesting findings that we're seeing with this program. As well, I just want to take the opportunity, this is the part of my talk that I thank all my volunteers. Citizen science is a great opportunity. If done correctly, it's a great opportunity for people of the scientific community to get with the general public to both collect data and you know, help research towards the same mission. So I just want to take the opportunity to thank all the volunteers that are part of our water quality program and that have definitely helped me out along the way. So I think with that, I will take any questions. Yeah.
Cool. Can you guys hear me?
Yeah.
Okay. Thanks, Nate.
Yeah, of course.
I'll go ahead. Oh, Lisa, if you want to go ahead and share the poll. Yeah. We forgot last time. Um, anyway, if anybody has any questions, again, please feel free to enter it into the chat. Nate, I just started off with just a brief question about citizen science water quality programs in general. Are there any other programs that are similar to FOS's, and have they have you found that they've done a similar analysis of their data to compare to, say, reference stations or other agency or scientific institution data?
Yeah, that's a good question. I know that there are a couple other citizen science water quality programs that are out there. Ones that come to mind, I know the Marine Resource Council either has had or still has an active citizen science. And I've been meaning to try to reach out to them to see if they've done anything as far as comparing it against their other monitoring systems and or agencies. As well as I know Team Orca, they have their Kilroy system, but they also have some citizen science that they do around Martin County too. But I don't think that they have compared it. They're more collecting, they do a lot of sediment work, and water quality is just a small section of it. So I don't know, but I definitely uh, want to reach out to other organizations, nonprofits that have these citizen science groups and kind of see what ways that I could, if they've done this before, see if I could further validate it using what they've done, or maybe I could, bring what I've done to them to see if I can get, we can test their data too. So yeah, definitely open to collaborations and such. But yeah.
Yeah, it's a great reminder. MRC, basically collects FOS's program was evolved from MRC, so the data would be very comparable for a lot of it, and probably get you into the northern parts of the too. So Bill Klein has a question here. His question is, what were some major changes between 2009 to 2013? Was there a major development that added roads, buildings that would absorb heat during the days and give back during the night?
Oh, wow. Yeah, that's an interesting question. That's a good question. Um, I would definitely say that throughout the years, I mean, we've been getting more development. So having more infrastructure that's created in the district, the difference in heat distribution to water and kind of land, and specifically cement and other impervious layers, could definitely affect the overall temperature in the water, especially also, rain patterns and whatnot. Um, I guess when I was first looking at this and I saw that interesting temperature rise during that period of 2007 to 2016, my mind went to, some of the big, I'm a seagrass person. So I was thinking we lost a lot of seagrass. We had a lot of different water quality issues that were occurring. And I wonder if temperature maybe played a small role in that. This was before my time studying here, but I think it was in 2000 and I might get this wrong, either 2011 or 2012, we had a huge algal bloom in St. Lucie that wiped out a lot of vegetation. So, but anyways, I think back to the biological, but from the infrastructure side of things, I'm sure that we've increased development, and that has a role to play as well.
Yeah, for sure. It might have effects on other aspects of water quality. I accidentally skipped over a comment that Jason had, and his comment is he finds the pH to be somewhat subjective with the phenol the phenol red method. Just wondering if you have any thoughts on that, Nate.
Yeah, that's something that we've been so our method of testing pH, we use the phenol red indicator, which is basically you're taking your water sample, you're mixing it with your phenol red, and you're using a color gradient to compare your end results, your pH unit. And that's one of the things about it is it is subjective because we've gone out a lot of times to where you can't quite match up the colors to it. And so at the end of the time, you kind of use your best guess. And the accuracy on those little test kits are about 0.2 rather than some of these other monitoring stations. And people who use probes, are able to get accuracy 0.01. So that's something that definitely acknowledged. And in the future, I would like to be able to incorporate actual probes, because pH is one of those things where having as much accuracy as you can is definitely beneficial. So we realize that the phenol red is subjective / might be giving us elevated results compared to the other stations, and I'm hoping on working on a different method or a solution to that. No.
Thanks, Nate. And then Jason actually has another observation and a question about dissolved oxygen. He observed a drop in late April through early June. And then he learned today, thanks to you, Nate, that this may be a normal seasonal shift. But is there any contribution from the Lyngbia bloom that he has observed?
Ooh,
I guess with respect to dissolved oxygen.
Yeah, that's a good question. So, dissolved oxygen is very dependent on temperature, just to start off with. So, during the hot summer months when temperature is higher, you basically have less dissolved oxygen is actually or less oxygen from the atmosphere is able to dissolve into the water. So that's why in colder waters you can obtain DO concentrations that are way higher in warmer waters. In addition to, you'll notice that if you test DO throughout the day, if you're testing DO at the end of the afternoon where the sun's been up all day, you've had a lot of vegetation and other contributions that increase the DO, and then during nighttime or first thing in the morning, you'll know that DO is low just because it's gone all night without photosynthesis and respiration rates are high. However, so that's kind of the normal process of DO. But I mean, when you start incorporating the breaking down of plant material and organics, that all those processes of decomposition, that process requires dissolved oxygen. So, for example, why we typically see these hypoxic events after an algal bloom, if the algal bloom is non-toxic, we don't really, if it's a non-toxic algal bloom, the toxins aren't killing the fish. What typically happens is when that plant matter starts breaking down, when it decomposes, and if it's on a hot summer day and maybe there's cloud cover, or maybe it's in the middle of the night when you don't have a lot of photosynthesis and you're just losing all that dissolved oxygen, that's kind of when you start, getting those fish kills, is decomposition plus some of the other environmental parameters that affect DO. So the answer about the Lyngbia is, it's funny because me and Jason have talked about this before, but as the Lyngbia, which is like a cyanobacteria-like algae, it proliferates on the sediment, actually photosynthesizes, fills up with air, and then kind of moves in mats, and then deposits that, and when it deposits back down, you can see it become breaking down. So I wouldn't be surprised if that's affecting the DO, but I'm not 100% sure. But when anything decomposes, it takes DO to do that. So
sure.
Yeah.
not seeing any more questions. First, Jason, did I get that question correct? Just want to make sure I asked what you.
Yes, I appreciate it.
Yeah.
Yes, thank
Okay.
you. Thank you, Nate.
Yeah.
Wonderful.
Yeah, of course.
Thank you, Jason. And I think we're almost at the end of time, but if I think if we have any other questions, you can enter them now or unmute yourself. If we'll put this, we're recording this now, and we'll put this on YouTube, hopefully within a week or two. And thanks everybody for
Well,
tuning in. Really
yeah,
appreciate it.
thanks to Nate and thanks to all of the volunteer water quality monitors who've made this work possible.
Thanks for
See you all in August.
Yep.
Yep. Thank you, Nate.
Yep, of
Really
course.
appreciate it. All right. I'll go ahead and